Alright, so now let's look at the performance characteristics of second order instruments. In case of second order instruments, these types of instruments actually, because of their design, they follow an equation like this. So you have second order differential, the output. For general engineering systems, and what we'll assume this to be not existing, and only this part exists, that the input change actually has in the form of steps. So this equation actually would reduce to thereby. Alright, so this can be even simplified to as A2. So then this can be even put it in this form. So the relation between output and input is given by. This can be simplified in this form. So we're writing this in the more standard form, where capital K actually refers to the sensitivity of the instrument. You can also refer to as static sensitivity. Omega n square actually is given by A naught by A2, which is the undamped natural frequency of this setup or the instrument. Zeta is equal to. Alright, so this is how our second order system looks like, or you can say second order instrument would look like. So it has obviously components of static sensitivity, it has a component of the frequency, it has a component of actually the damping ratio. Alright, so this is nothing but a relation between output and input, actually, which tells us this is the measure and this is the output value from the instrument. But it obviously follows this type of characteristics, which means it will have some sort of something called a static sensitivity, it will have frequency, it will have a damping ratio. Because of this will have different response for different types of damping ratios, different frequencies, and obviously for the static sensitivity. Now the examples of such systems which follow this type of actually, a U-tube manometer is a good example of such system, where you have obviously the liquid inside the manometer actually, which has some particular mass. So as there is change in the pressure, obviously between the two ends, this will flow as per the change in difference in the pressure and accordingly take some height. Because this is a fluid and it has some mass, and because of change in the pressure, actually this will start kind of oscillating until it actually reaches something called a steady state, and this is how dynamic behavior of this instrument actually affects the time it takes for the output to faithfully respond to the input. So because of this type of instrument, this type of design will have such issues for second order instruments, because there is mass. Similarly, an example could be of an accelerometer that we use in our day-to-day life. In our mobile phones, we have accelerometers. So this accelerometer actually is a MEMS-based accelerometer, which is highly complicated. But the basic design of an accelerometer consists of the seismic mass, and you can have a piezoelectric material, and the seismic mass being fixed to the base. And the moment this setup starts vibrating, and accordingly there are actually this stress is created on the piezoelectric material, according to which actually it gives a signal which can be amplified, and we can actually find out the acceleration. Now this type of instrument, which here is an accelerometer, actually is again a second order instrument, because there's a mass, there's some sort of damping, there's some sort of stiffness of this material. All those things actually together form as a second order system. This can be more seen in line diagram way this way. You have a proof mass or a seismic mass, you have some stiffness, and you have some damping associated. So again, this makes it a second order instrument. Here we consider an example of a second order instrument as to show the values of the parameters of the instrument actually that actually correspond to the natural frequency, the damping ratio, and all those parameters that we see for second order instruments. Now we have a spring based force measuring instrument, where we want to measure a force Fi, and we have installed a spring here which is held over by some mass m. So because of this force, this obviously would compress and then extend back upwards, and accordingly as per the force it would actually stop at a point which is which actually is calibrated to give the amount of force that's being applied. Now this force obviously could vary also. Now if we want to write or want to model this type of instrument, obviously we need to know the dynamics behind, or the physics behind this type of equipment. and or the instrument. So this instrument actually would have some mass m, and it would have some stiffness k. It may also have some damping c, damping coefficient. Now we can use in the Newton's law actually to basically find out the equation of motion of the spring on the application of the force. So let's assume it moves with some displacement x and has some velocity and an acceleration. So accordingly, summing the forces, we will have mx double dot plus cx dot plus kx would be equal to the force applied. So now this is a very popular equation of a spring mass damper system with a forcing function. This is how the instrument is actually modeled, and obviously we can also find out this by simple Newton's law by balancing the forces on the inertial forces and the applied forces. Now let's assume we get this type of equation for this type of the system, second order system. Now this is second order, this is a second order differential of the position, which actually is the acceleration. For this instrument, actually, if we want to put this in a very standard form, the way the second order instruments are put in, so we can put this now in this form: m d square plus cd plus k into x is equal to f of I, and accordingly we get the transfer function, which is actually the output upon input, will be equal to 1 upon md square plus cd plus k. Now the standard form of the second order systems is actually this way. We can maybe put it again: k upon d square by omega n square plus 2 zeta d upon omega n plus 1. Now if we compare these two, k equal to 1 upon ks refers to stiffness of the spring, and we would get omega n, that is the natural frequency of the system, is popularly called k by m. So we can refer it as ks by capital M, and the damping ratio is given by c upon 2 under root of ksm. All right. Now these are the corresponding parameters of the second order force measuring instrument. Now you can clearly see that this is the static sensitivity of the spring, which will actually depend on the stiffness of the spring itself. The natural frequency of the spring would depend, or this instrument would depend on the stiffness of the spring also, and also on the mass that is attached over the spring, or the spring or the mass, which includes the spring or the mass also. And the damping ratio would depend on the damping coefficient and the stiffness and the mass together. Now, with all these three being the physical parameters of the instrument, we can change these values and the design of this in this type of instruments to get a desired performance. For example, if we want to know the response of these second order systems now, so we can use the values of the stiffness, mass, and damping, and accordingly find out the response of the second order systems. So this is how the step response of second order systems would look like, similar to what we have just now seen for the spring force measuring spring system. Now this is plotted with respect to the ratio of output input, and this is q naught by k qi, which for us would be actually x naught by k f, because f is the input and x naught is the output, k is the static sensitivity, and it's plotted with respect to omega nt, which is nothing but the natural frequency into time, because these two appear in the equation. Generally they appear in the complementary function, and the particular solution of the differential equation, they appear together. So we would generally use omega and t together. So this is how the instrument actually responds. So it oscillates, goes from maximum to minimum and oscillates, or for some other cases it just oscillates to some extent, then almost damps out. But there are instances where it just follows the output. So all these actually vary with respect to zeta. Now, obviously, the parameters that we have with us is zeta, omega n, and the k. Okay, we have already put up here. So what we are controlling is actually zeta and omega n. Now we can see, as per the solution of the differential equation of the second order system, this is how it would look like. So if we have zeta equals to 0, which is an undamped system, so then we will see there will be continuous oscillations. We won't get the correct value of the desired, we won't get the correct desired output. for the corresponding input. So we would always have oscillation. So this is very highly, or you can say highly undesired. As we increase zeta, that means as we increase damping in the system, or you can say damping ratio, so this starts decreasing. So we see that the as for zeta is equal to 0.2, this now has a lesser amplitude ratio, which is quite desired. And then as we go on to zeta is equal to 0.4, we increase zeta to 0.6. So now you see, as the zeta increases to 1, even to 1, so we have almost the less oscillations in the output. But mind you, this is also you have to be careful while designing these instruments. This is at the expense of the delay. Now see, for zeta is equal to, which is undamped system, you get rise to the desired output very quickly. So which is, let's say, at t is equal to omega and t together is equal to 1.5, which is quite fast. But for zeta is equal to 0.8, where you may see that there is least oscillations in the output, but this happens at around omega and t is equal to 4. So this is kind of a compromise on both zeta and on both time, this time constant, or you can say the natural frequency of the system. So that's why there's a compromise, when you design these systems on these parameters, whether you need to increase the stiffness, you need to increase the mass, you need to increase the damping. So all these have to be done together in such a way that you get the best performance. Usually in engineering systems, we use zeta is equal to 0.6 to 0.8 more preferably are used as the trade-off. Otherwise, we have some system where we have over-damped systems where it's almost equal to 1.5 or even 1, where it almost doesn't even oscillate, but it maintains a constant gap between the input and the desired output and the output by the instrument. There are systems called critically damped also, where it almost touches the line, but sometimes we compromise with all such factors and then try to put this to around zeta is equal to 0.6 to 0.8 is the most desired values. Now this will be clear also from the frequency response of these second order systems. Now this is how it looks like. So you have the amplitude ratio between the output and the input, and then you have the ratio of the forcing, the frequency of the input to the natural frequency of the instrument. You can say the frequency response transfer function, where we substitute capital D by I omega, and then we actually try to find out how it actually responds to the forcing function, where the forcing function is usually having some obviously frequency component. It is very time varying, and we see how the output responds. Now, if you carefully look at this type of output frequency response, this you might have even observed. Usually, we see this in mechanical vibrations course. We study this type of plots. Vertical axis, we have the ratio of the output to input. On the horizontal axis, we have the frequency of the input to the natural frequency of the instrument that we have designed. Now, as you see, the ratio should preferably generally be equal to 1. Or you can say like this. This should preferably be 1 for an instrument. Now, for 1, we are seeing that it should be somewhere here. Now, obviously, if we go beyond this value, this is quite low. So, omega n, which means if we design an instrument, because input we may not be able to control, but instrument, that is omega n, we may be able to control, because omega n is nothing but k by m in this case, which k for the spring, we can design a spring of different k's and different m's. So omega n is in our control. So the more the omega n, actually the less the omega by omega n ratio would be, and the less the ratio would be, the more we are actually into this range of 1. But at the same time, we have to be careful about the damping ratio also. So if we again keep zeta is equal to 0, so we will have amplification, huge amplification, which is almost a resonance, where we the frequency of the forcing function is equal to the natural frequency of the system, so it resonates, and we can have very high amplitude, which is again undesirable. So we would like to keep zeta around 0.6 to 0.8, where it almost follows a flat curve here for 0.6 to 0.8, and then keeping omega also equal to omega n equal to very high, so that this whole ratio is less than 1. So this is where we actually would like the instrument to be designed for. And this is also evident from the phase response, or the the phase angle between the output and the input that we see in the frequency response functions. This is the ratio again, omega by omega n on the horizontal axis, and we see that for resonance again we have a minus 90 degree phase shift, But as we go beyond this value on this side, so there's a huge phase difference between the output and the input. So as we desired, so we would like to have it between 0 to 1, and between 0 to 1 we would like to even put this into this range where there is a flat curve between the phase angle and the omega n ratio, which is this one, and this corresponds to actually zeta is equal to 0.6 to 0.8. Fine. So this gives us the most convenient form of output. So that's why in most of the cases we would have this between 0 to 6, 0.6 and 0.8. So this is how we can design, because zeta for us is equal to damping, which is in this case C, the damping, and the damping coefficient divided by 2 under root of K into M. So we have all the three parameters of the spring in this. So we can design this zeta in such a way that it equals to 0.6 to 0.8. And also the omega n actually is the more and more. So accordingly, we design our instruments so that they have a performance in this range. And this is what is actually desired in the design and the analysis. All right, so we'll see these things more clearly in the design of instruments for motion measurement, where we'll have accelerometer, measurement of acceleration, and other parameters. We'll see these things in more detail in there. Thank you.